In the previous lecture, we know how to obtain a measure from an outer measure, and that is simply by restricting the outer measure to the set of measurable sets in the sense of category. So in this lecture, we would like to discuss how to create an outer measure based on a pre-measure. And this will be the content of the following theorem. So suppose we have a triple. So X is a set, R is a ring, and mu is a pre-measure. So this triple will be our pre-measure space. Then we define mu star on the set of all subsets of X as follows. So given an A, which is a subset of X, the outer measure, or mu star of A, is defined to be this infimum here. So first, you take a covering of A, where the sets A sub n are in the ring for all n. You take the measure or the sum of the measures, pre-measures, and then among all these numbers, among all these possible coverings, take the infimum over all these sums. And to have an idea what is happening in the definition, suppose we have a covering that consists of, let's say, three sets, A1, A2, and A3. And these are in the ring. So here A is covered by three sets, okay, A1, A2, and A3. So if you take the measure of these sets, imagine area for instance, then there would be duplications and there would be excess. So for simplicity, let us call these regions here the excess parts. So these are the excess of the covering. So this is the difference of the covering with the set A. And in this case, you see that the sum of the areas of A1, A2, and A3 is larger than the set being covered, in this case A. And we want to minimize that excess area. And that is basically what we are doing here. So we take the smallest, or the more appropriately the infimum, over all this sum of pre-measures. So our covering can be countable. So that is the definition of mu star, and we follow the convention that the infimum of the empty set is infinity. This is the case if it is impossible to cover A by a countable collection of elements in the ring. So if there's no such covering exist, then we define the outer measure of the set to be infinity. So indeed, this mu star is an outer measure. If we take the restriction of this outer measure with the ring, then we get the original pre-measure mu. And all elements in the ring are measurable with respect to the outer measure mu star. Okay, so this theorem tells us how to construct an outer measure from a pre-measure. And according to the second or third properties, okay, this outer measure is an extension of your pre-measure. So let us look at the proof. So the first part is to show that indeed a mu star is an outer measure. So the collection consisting of only the empty set, and because we have a ring, the empty set is in the ring. This covers the empty set. By that, we mean that empty set is a subset of itself. Then mu star, which is the infimum, is now 0. Because the smallest, according to the definition, the infimum, so 0 is a lower bound of this collection. Since a premeasure is non-negative, so the smallest value of the premeasure is indeed 0. Here we have a covering whose sum of outer measure is 0. That is the empty set. Okay. Then this implies that the lower bound 0 is attained. So therefore, the outer measure of the empty set is 0. Now let us take two subsets of X, and A is a subset of B. Observe that any covering of B is also a covering of A. But not the other way around. So there can be a covering of A that is not a covering of the larger set B. In other words, there are more coverings of A than coverings of B, since any covering of B is also a covering of A. So by the definition of the infimum of a larger set is smaller or possibly equal to the infimum of the smaller collection. Since there are more coverings of A, then we obtain that the outer measure of A having a more covering is less or equal to the infimum of the sum of measures of coverings of B. So this is monotonicity. Now let us prove sub additivity. And we will show the following. So suppose I have a collection of subsets of X, A sub n. We would like to show that the outer measure of the union is, let's say, what? Less or equal to the outer measure, or mu star of an, since we are not yet sure if it is indeed an outer measure. So mu star of the union is less or equal to the sum of mu star of an. Okay. Take note that if A naught is a subset of X and A naught is contained in the union, then by monotonicity, mu star of A naught, we already know that mu star is monotonic, it's less or equal to mu star of the union. And according to the one that we wish to show, this is less or equal to the sum of the mu star of an. And take note that this is what we have defined to be sigma sub additivity. Okay. So it is enough to establish this part here based on this discussion. Now, without loss of generality, suppose that the mu star of an is finite for all n. Note that if for some an mu star of an is infinity, then this would be infinite, and the inequality is obvious now. So it is enough to assume that mu star of an is finite for all n. Now, so for each n, we can find a covering, let's say b and k from 1 to infinity, consisting of elements in the ring, say b and k, that covers the set an, and okay, the outer measure plus some positive number, say epsilon, okay, and we rescale this epsilon by dividing by 2n, okay, and that would be clear later. In fact, you can take any series that will converge to 1. In this case, let us take the geometric series 1 over 2n. So what is epsilon? Let us take an arbitrary positive epsilon. Now, this outer measure of an plus epsilon over 2n is larger or equal to the sum of the premeasures of b and k from 1 to infinity. So what we did is that we take a specific an, take covering consisting of elements in the ring of this set an, wherein if I add by epsilon over 2n to the outer measure, or mu star of an, then this must be larger than the sum of the outer measures, or the sum of the premeasures of the covering. And this is basically obtained from the definition of the infimum. Okay, if you are not familiar with that, okay. Indeed, suppose on the contrary that we cannot find such covering. In other words, for every, so taking the negation of that statement, for any covering of an, we have the following inequality. Suppose that we cannot find a covering that this is true. In other words, all covering should satisfy this one, 2n, okay. You now take the infimum over all such covers of an. So the infimum on the left-hand side would be the outer measure of A by definition, or an, I should say. So that would be the inequality, and you can see that this would imply, since 2n is positive, you can cancel this 2, multiply by 2n, and you end with epsilon being less than or equal to 0. which is a contradiction to what we have taken a while ago. That epsilon is positive. Okay. So visually, this is what we did. We did. So suppose this is mu star of an. Now, let us add a small number. Okay, and then by zooming in, let us say this is that number. So the distance here is positive, in particular epsilon over 2n. So we did find a cover wherein the sum of the premeasures of the covering is less than this point here. So that is slightly larger than the outer measure of an, or mu star of an. So we picked a covering that is less or equal. The argument presented above is the following. What if all covering would be larger than that value? So in other words, all covering should be an element above this apart. So that in that case, this would imply that this would be the infimum, okay? Or this would be at least a lower bound, which contradicts the fact that this is the smallest lower bound, or the greatest lower bound, the infimum. So here we found a larger infimum than the one provided by the definition, which is a contradiction. So that is basically the proof of the theorem, or the proof of, I should say this remark here, that we can find a covering that is less than a number that is slightly larger than the outer measure of an. This is, let's say, slightly larger than the infimum, which is mu star an. Okay, since the Bn case, k from 1 to infinity, covers an, if we collect those, so B and k, now n and k are both integers. By construction, these are elements of the ring. This will cover the union. Okay. And if we apply the sigma, or apply the definition of mu star of the union is less or equal to the sum n and k from 1 to infinity of the premeasures of the covering. Take note that mu star of the union is the infimum of all such summations. So the infimum is smaller than this particular sum. So definition of mu star. Next, we split the sum into two parts. Okay. Now, one can do this because, let's say, if this series here is convergent, then you can rearrange the terms, because that would imply that this series is absolutely convergent due to the fact that the pre-measure of a set in the ring is always non-negative. So convergence is equivalent to absolute convergence. And in that case, you can rearrange the double sum in this iterative sum. Well, if it happens that this series is divergent, so all of the succeeding terms would be infinite, and still we have this inequality. So you can rearrange the terms, and well, based on our discussion a while ago, this Bn case here is less or equal to the outer measure for mu star of An plus epsilon over 2n. Okay, so that's the sum. That's already the sum, okay? And so that's the inner sum, and let us just write the outer sum in this case. So therefore, if you distribute the sum, this is now less or equal to mu star of An plus, so as I said, you have here a geometric series, so the sum would be epsilon. And since epsilon is arbitrary, we can pass epsilon to 0 to obtain sigma subadditivity of mu star. Okay, so that's the first part. So again, I recall that mu star of the empty set is 0. Mu star is monotonic, and it is sigma subadditive. Hence, mu star is an outer measure. And that is the first part of the theorem. Now let us move on to the second part. And that is to show that the restriction of the outer measure on the ring is equal to the given pre-measure mu. In other words, the outer measure of A is the same as the pre-measure of A for any A in the ring R. Okay, so let's start indeed with an element A in R. Since this single collection, or this collection consisting of only one element, and then you take the rest to be empty, of course. This one covers A, and therefore the outer measure, which is the infimum of measures in the covering, is less or equal to this specific pre-measure of A. So since we only have one set here, well, technically you need to add empty sets, but since the pre-measure of the empty set is 0, so we did not include them here already in the covering. So by the definition of the outer measure being the infimum, so mu star of A is less or equal to mu of A. So that's one inequality. The next one, okay, so take a covering. say A sub k of A, consisting of elements in the ring. Okay. By this, we mean that A is a subset of the union. Since A is in the ring, this implies that take that mu is sigma sub-additive. A premeasure on a ring is sigma sub-additive, as we have shown in the previous lectures. So here, the premeasure of A is less than or equal to the sum of the premeasures of A sub k. Okay, so from this, we could now take the infimum over all such covering A. So the infimum of the left-hand side could be the outer measure of A. So we have this. The outer measure is less or equal to the premeasure and vice versa. Hence, we have this equality. So this is the second part. The restriction of the outer measure on the ring is just the premeasure. For number 3, we wish to show that all elements of the ring are measurable with respect to the outer measure mu star. So that let us take an element of the ring, and we would like to show if this is indeed measurable. Take a test set, okay, E and X, and take a covering not on A, but in this case, of the test set. Then, okay, let's start with the sum of the premeasures of the covering of E. So this is the sum of AN. So the idea here is that after taking the infimum, this would lead to mu star of E later. So first, let us start with this sum. Okay. This is equal to a premeasure is additive. Therefore, mu of AN, we can write that as A intersection AN plus A complement intersection AN. So we just split AN into two parts. The set wherein the elements are in A and those that are not in A. So hence the union would be A sub n. And then you still have a sum in here. Since AN is in the ring, A is also in the ring, and the ring is closed under finite intersections. This is in R, and it's closed also under complementation, so this intersection is also in R. Okay. The important part that we would like to mention here is that A intersection AN okay, we know now that this is a collection of elements in the ring or sequence of elements in the ring, and this is a covering of A intersection E. Because if you take the union of the A sub n's, uh, it will contain E. And in a similar way, A complement intersection AN, this sequence are sequence of elements in the ring, and it is a covering of A complement intersection E. Now, if we split the sum into two parts, this part and then this part, the first one would be, since this forms a covering of A intersection E by the definition of the outer measure is less or equal to the first sum. And then, similarly for the second part, second sum would be greater or equal to the outer measure of A complement intersection E. So we use these two parts here, add the definition of the outer measure. As mentioned a while ago, what if you take now the infimum over all such covers of E. In other words, I take the infimum of this over all AN, a collection of elements in the ring that covers E. That would be the outer measure of E. And let us just write the other term. So that's 1. There's a correction here. This should be E. Okay. And take note that this is valid for all E, since E was taken to be an arbitrary subset of X. This implies that, okay, A is indeed measurable. And that ends the proof for the third part and hence the theorem, since, okay, we started with an element in R, we showed that it is measurable, hence R is a subset of the collection of measurable sets. Okay. So going back again with the theorem, statement of the theorem. So if you have a premeasure space X R mu, you can define the outer measure in this way. So take a covering of your set A, but the sets should be in the ring, A sub n. You take the sum of that, okay, and then take the infimum over all such a possible sums. And here, this is an outer measure. It extends the premeasure, and all elements in the ring will be automatically measurable with respect to this outer measure mu star. And now you could see why is it called an outer measure, because here the outer measure is based on taking the infimum of the sum of premeasures of the covering. So we take the outer measure by taking the infimum of the measures that or pre-measures of the covering. So here you can have excess because our covering in general can be a larger set compared to the set A. So we take the measure from, let's say, above. Before I'll discuss how this is connected to our extension problem, let me mention an alternative formulation for the outer measure. So this is alternative formulation of mu star. So the outer measure of a set A is also equal to the limit of the following set of, or the infimum of the following set of numbers. So first, you take the covering. Let us use a different notation here, Bn. But Bn is increasing. Of course, these B sub n's are also in the ring. As this sequence is increasing, and we can take the limit, okay? It will increase, and in that case, this one is equal to, quote unquote, okay, mu of the union, okay? So the limit of the pre-measures of the increasing sequence is basically the limit of the sequence. In this case, that is the union. Well, there's a quotation marks here because we are not guaranteed that this is in the ring. So you cannot apply it into mu. Okay, but the idea is that. Okay, so instead of taking the sum, if you have an increasing covering of A consisting of elements of the ring, then you can simply take the limit. And I will not provide the proof. If you are interested, there is a proof in the course notes, and you can look at it. Okay, so now let us consider our extension problem. So let's just say this is the solution to, or the answer, to the extension problem. And in fact, these are two statements, but let me collapse them into one. So this is the, let's say, Karatyodori-Han-Kolmogorov theorem. So let's start with a pre-measure space in the extension problem. So X R mu, where R is a ring on X. Then, so the first part is the Karatyodori theorem. there exists a measure space X sigma gamma such that R is contained in sigma and the restriction of gamma to R is the premeasure. And this is the uh, existence of our extension problem, extending the premeasure space into a measure space. The second one, if let's say in addition, our premeasure space is sigma finite, okay, then there exists, okay, in fact, a unique measure space, let's say X sigma R lambda, such that lambda restricted to R. So the restriction of this measure lambda in the ring is the same as the pre-measure. Okay. So here we have a specific sigma algebra, and that is the sigma algebra containing R. So the first one deals with the existence of the extension of a pre-measure into a measure. The second one is the existence and uniqueness of the extension if or as long as this pre-measure space is sigma finite. And here, the sigma algebra is restricted to the sigma algebra generated by the ring. And this gamma here will be called the Caratidori extension. Of your pre-measure mu, while lambda will be called the Han-Kolmogorov extension of mu. So take note, there's a difference here. First, here mu is assumed to be sigma finite. In the first case, it is not necessarily the case. Here, the sigma algebra is a sigma algebra containing R. Here, we have a specific sigma algebra containing R, and that is the sigma algebra generated by R. So that's the differences of the Caratidori and the Han-Kolmogorov extensions of the pre-measure mu. Now, with all of our efforts, you could see that the proof is in fact straightforward. And why is that? So for the first one, you can take sigma to be the set of all measurable sets with respect to mu star. What is this mu star? So if you have a pre-measure, you can generate an outer measure according to our previous theorem. And with this outer measure, we can collect all measurable sets with respect to that outer measure. And as we know, that will form a sigma algebra. Now, how do we create the measure? Well, you simply take the restriction of the outer measure to the measurable sets. And we established also in the previous lecture that this is indeed a measure. Okay. And going back with the proof, are we sure that R is in sigma star? Yes, according to what we have established in the previous theorem as well. So we have this. How about the restriction? Okay. So if you restrict the outer measure on the ring, we get the pre-measure. And that is, so going back with the statement, the second part here. So the first statement of the Karatodori-Hahn-Kolmogorov theorem can be established by simply taking the sigma algebra to be the collection of all measurable sets induced by the outer measure mu star corresponding to the pre-measure mu. And the pre-measure gamma is obtained by restricting the outer measure to the measurable sets. Okay. How about the second part? The second part, well, uh, first, take note that R, the ring, okay. But before that, let us apply. Here, 1. In other words, apply 1 by taking. So what would be the measure lambda? Lambda would be simply the restriction of gamma to the sigma algebra generated by R. And for uniqueness, you can apply the uniqueness theorem that we have discussed earlier. Okay, but am I sure that this is contained in this set? So we are asking if the ring generated by R are all the elements are all measurable. Well, that is indeed the case because we know that R, the elements of the ring, are all measurable. Okay, since sigma of R is the smallest sigma algebra containing R, and this is a sigma algebra containing R, therefore sigma of R is a subset of this sigma algebra. So we can indeed take the restriction of gamma. So take note that gamma is defined on sigma, which is sigma mu star. So if you restrict the gamma on the sigma algebra generated by R, that would be a measure, of course, because gamma is a measure, hence the properties of a measure will be inherited to lambda. And that will be the measure for this measure space in the second statement of the theorem. So in other words, you can think of the Hahn-Kolmogorov extension as a restriction of the Karatodori extension. And that's is the solution or to the answer of our extension problem. Is it possible to find an extension? Yes. And is it unique? Yes, provided that our first or our starting pre-measure space is sigma finite. So in this part, let us summarize what we have discussed so far. So going back to a semi-ring H, and we have, let's say, a pre-measure nu, define on this semi-ring. Okay, let us move this a bit. According to Hans' theorem, well, we can generate the ring and extend this pre-measure nu to a pre-measure mu on the ring generated by the semi-ring. So this is also a pre-measure, and you have here the canonical injection. So what we did is to start defining an outer measure, let's say mu star, corresponding to this pre-measure mu. Then take the measurable sets, sigma mu star. Of course, these are all subsets of X, so you have here the corresponding canonical injection. This map gamma here will be, which is basically the restriction, okay, of the outer measure to the measurable sets, is now your Caratodori extension of mu. As we know, the set of all measurable sets contains the sigma algebra generated by the ring, generated by the semi-ring H, and well, it can be shown that this is nothing but the sigma ring generated by H. So here you have your canonical injection and another canonical injection here, sigma H. If you restrict gamma on this ring generated by, or the sigma algebra generated by the ring H, then you get the, in this case, what's the notation? Lambda. Yes, lambda. This is now the Han-Kolmogorov extension of mu. This lambda here. Okay. Oops. So to summarize, that's the construction that we have developed in all of our discussions so far. So to reiterate, you start with a semi-ring. Suppose that you have a pre-measure, okay, and this, let's say this pre-measure is sigma finite. Now you extend your pre-measure on the semi-ring to the ring generated by H, and that would be this mu. So you can go from H to rob H to the set of non-negative integers, and that would be your pre-measure. So in other words, the pre-measure nu is the restriction of your pre-measure mu on the ring. Well, to create the two measure extensions, you first create this outer measure, mu star, associated with this measure mu. you restrict the domain, okay? Instead of considering the power set, you consider the measurable sets corresponding to mu star, and the restriction of the outer measure, which we denote by gamma, is the keratodory extension measure corresponding to mu. We know that the sigma algebra, sigma mu star, that is again the set of measurable sets, contains the sigma algebra generated by the ring, generated by the semi-ring. And as I said, that would be the same as the sigma algebra generated by the semi-ring H. And these two are the canonical injection maps. And finally, by restricting your keratodory extension to the sigma algebra generated by H, you get the Han-Kolmogorov extension, which we denote by lambda. Okay. So there are, in this case, two measures or measure spaces that we have developed. One is the via the keratodory extension, and the other via the Han-Kolmogorov extension. In the succeeding discussions, or in the future lectures, we would like to see the gap between these two. Are these two sets equal, or are they different? But that would be the topic for future lectures. In the next lecture, we will apply this in constructing the Lebesgue measure on Rn. See you there.